All right. So we're going to pick up uh, the rest of the PowerPoint that is talking about the SIR model. And we're going to pick up right where we left off on class on Wednesday. And as you might recall, on Wednesday, we were talking about this new term, the RO term or the R naught term. And R naught is, in effect, a function or a factor of how infectious something is over how easy it is to get people from being infected or the infectious force to the recovered population or the removed population from the equation. So alternatively, again, if we can denote what an R naught is, and we know the general um, gamma of this equation, i.e., the time it takes to recover from that particular infection, we can also back calculate what the beta or the force of infection is because we know the infectivity of the actual infectious agent. So, gonna head back to where we were on Wednesday, which is that there are epidemiological implications that we can understand and put into practice if we understand what the R naught of an infectious agent is, or if we understand what the gamma term or the beta terms are. We can use two of these pieces of information to figure out the third. And the general idea here, and the reason why RO and beta are so important in understanding infectious diseases is, as you might imagine, the larger the beta term is as the numerator, right? Because beta over gamma equals R naught. If the infectivity of a particular infectious agent is higher than the ability for a host to remove it, the bigger the infectivity is considered to be. Just as if we have a high infectivity quotient or a high infectivity um, consideration for an infectious agent, this then divide multiplied by the number of days you are infected gives you the general idea of how many days you would be infected, or otherwise known as the force of infection of an infected from an infectious agent perspective. So we consider the R naught of a great many different kinds of infections. The highest or most infectious of these infectious agents that we know about is measles. And the interesting thing about measles is when we think about measles, that we have an excellent vaccine, the MMR vaccine. And the MMR vaccine has allowed measles to go eradicated in many developed nations to the point where there is a high level of herd immunity in relationship to its high infectivity. So the reason that we don't hear about outbreaks of measles until recently is that we places that had good vaccine coverage were able to get a good amount of herd immunity. And when you have a high amount of herd immunity, irregardless of what your R naught value is, the infection, or the force of infection, the beta value is going to be much lower, because the susceptible, right? Because you have a susceptible population, I, and then R. Your susceptible population is significantly reduced when you have something like vaccines or if you have something like another interventive strategy. This is something that we talked about on Wednesday, which is in order for the SIR model to work, we have to have acute infectivity associated with infection, and that infection more or less coalesces with the amount of the ability to be contagious. And so that is true for a lot of these diseases you see here, like measles, diphtheria, polio. But the biggest problem for these, as far as fitting them to the SIR model, is that we have a great number of different kinds of interventive strategies that either generate herd immunity um, or have other types of treatment. So when we consider the SIR dynamics of a particular kind of infectious agent, typically, if we think about the S part of this, right? S, I, and R, the susceptible population is typically any number of individuals that, again, could be infected by a particular kind of infection. And not surprisingly, as we start with 0% resistance or 0% removal, as the number of individuals move into the recovered phase, this starts the same number of susceptible individuals will also decrease because as you are either being removed from the population of potentially being infected um, versus not being able to be infected, or if more importantly, you have a subpopulation of people who are being infectious, right? As this goes up, the susceptible number goes down because they're moving from the S to the I. But as you have infections go up, you get people who become resistant to that infection. They leave that population either through dying or becoming uh, convalesced from that particular infection. And when they become convalesced from that infection, either when we have infected individuals or convalescent individuals from being infected, the number of susceptible peoples goes down. But again, it's really important to remember that not all models are 100%, and most models aren't 100%, but they can inform us of particular pieces of information that can help us better understand the dynamics that an infectious agent has in relationship to its spread, its infectivity, and the likelihood it might cause something like a pandemic or an epidemic. So when we think about herd immunity and how it fits into the SIR model, right, we have to consider all the terms of the SIR model, including the fact that for an epidemic to occur, the R naught of an infectious agent has to be greater than one, just simply because it has to be able to have a numerator, right? The force, again, the force of infection, the beta, has to be higher than the rate of recovery or the number of recovered individuals, which is the gamma. So if we think about the susceptible population, um, and when we're talking about a particular kind of infection, or if we're talking about herd immunity, for for all of the people who have immunity to a particular kind of infection, let's say you had your vaccine against measles, you, because you've had a vaccine against measles, do not fit into the S naught model because you're not susceptible to measles because you've been vaccinated. And this is another important point, which is, we talked about how the SIR model fits under no inventive strategies, but the SIR model also gets affected, especially in the susceptible population, not because of the people who can get interventive strategies or interventions after the point of infection, right? Because if you've been infected, you move from S to I. But in reality, if you have something that completely prevents infection, you can affect the number that you start with, which is the S. So anything really, if we have an R naught that exists that is less than or equal to one, right? If we need it to be greater than one, and typically much greater than one in order for an epidemic to occur, but if it's less than one or significantly less than one, we consider that to have or be a disease in which the population that is typically susceptible, right? Not susceptible, but typically susceptible, experiences something known as herd immunity. So again, when we think about the SIR dynamics and what we talk about, part of the biology that you're seeing that's occurring during the SIR dynamic is as you're getting individuals who are infected and people who are becoming resistant or recovered from that infection, because they generate a certain resistance to that particular infection, they come out of the number of susceptible individuals, but also they don't rejoin the infected individuals. So the susceptibility goes down not only because you're taking numbers out of the original population, right? You're taking them out of the N, but also they're now moving into a different population dynamic. They're moving into the resistance dynamic, which does not put them back into this cohort. If if they went back into being susceptible to infection after they were sick, as this line would go up, the blue line would then rebound, right? Because if you're going from being sick or infected to non-infected but still susceptible, you get this. But instead, we have this third line, which denotes resistance to that infection. So when we have all this information, how do we know, or how can we utilize this information as relates to epidemics and pandemics? Well, we can use this information to get at what the likelihood of an epidemic or a pandemic is, but what if one is actually undergoing? And if there's already an epidemic that's already occurring, we can typically use all this information to get at another important piece of information, which is the effective reproductive number. The effective reproductive number is effectively how infectious a particular agent is multiplied by the number of susceptible individuals that remain in a population after the epidemic has started to occur, divided by the number of people in that population that the epidemic is occurring. Because again, this is an epidemic, not a pandemic. So we're looking at really a single population of which an infectious agent is coming through at a very rapid pace. So, so what does this mean? So what this means is when the effective reproductive number of an epidemic reaches less than one, right? Because it is in effect a function of the number of susceptible people divided by the number of people you even have. After you get under one, you're going to begin to have too few people left to be in the susceptible space. So the smaller the susceptibility, the smaller the susceptible number of people that exist, the smaller the beta becomes, and therefore the less people that can become infected. So the end of the epidemic that we can predict based on the SIR model really boils down to when we look at the original equation, right? The number of infected individuals that changes over the same constant of time is it has to reach zero. And the reason being is that when you reach zero, or the number of infected people becomes zero, if this is zero, right, then the likelihood is that beta now becomes zero. The force of infection is zero, and vice versa. So now this occurs for two different reasons, right? One really important reason why you have this type of curvature biologically is because over time, especially with something like a virus, viruses mutate. And when you have mutations in viruses or in other organisms, there is this constant pressure to increase infectivity and increase biological presence. But that doesn't mean that all mutations actually take off. And that is to say that sometimes you have mutations that occur that burn a particular infection out because they become a loss of fitness mutation. The other reason, the more human reason, especially when you're talking about infections in epidemics, is that as people are infected with infections or infectious agents, your body, if you for most people that are immune competent, begin to generate something called memory and protective immunity. So after you get infected with something, or if you're vaccinated against something, you generate these adaptive immune cells, these cells that can specifically be used to target a very specific infectious agent or pieces of an infectious agent. And when you generate memory, you basically scale that response. So the first time you see something, it might take about 14 days to respond. But the second time, so number one, right, you get a 14-day response. But the second time you see something, either after being vaccinated or having an immune response, it takes about 24 to 48 hours to respond. So you go from 14 days to about 1 to 2 days. And that difference in effectiveness and potency of immunity does actually provide another layer of resistance that diminishes the susceptibility pool of a particular infectious agent. This also can tell us a lot about something we talked a little bit at length about on Wednesday, which is what is the human concept or the human dynamic related to the SIR model? And this has to do with our behavior. And partly because for most organisms like bacteria, right? So you have bacteria, fungi, and parasites. This kind of works because, especially during a pandemic or an epidemic, these things are infecting a single population, typically humans or another population of animals. But for viruses, this really much does play an important role here. Because again, viruses, they require a host in order to divide and evolve. So when we think of the concept of flattening the curve, what we're talking about is how can we change our behavior, right? Our behavioral interventions that can reduce the R naught simply by changing the accessibility of an infectious agent to the host organisms that it requires to survive. So for viruses, this works because if you take away, say, like COVID, it infects humans. If you take away the human host and let everybody else who has the infection convalesce, there's nowhere else for it to evolve and infect. And in a sense, because you're changing this dynamic, right? The susceptible to infected dynamic, you're changing the beta. If you're changing the beta, you're changing the S to the I model, you have fewer I, so you have fewer people moving to R, which changes the gamma model. So when you have a change in beta and gamma, gamma is much bigger than beta, and therefore, if R naught is equal to beta over gamma, if gamma is now bigger, it's lowering the R naught of the infection. Now, does it lower the R naught of infection from the biology perspective of the infectious agent? No. But does it lower the R naught from the perspective of how infectious that agent is in relationship to the behavioral interventions we've introduced? The answer is yes. So the interesting thing is that there are a number of different models that the SIR model has been evolved into, including the SI model, the SIRS model, the MSIR model, et cetera, so on and so forth. But the cool thing is all of these models have one thing in common, and that is that they have some type of mathematical compartmentalization, meaning that we're looking at different compartments based on realized data in order to better understand the transmittance of those particular kinds of infections. So, per example, if we were to look at a compartment model for COVID-19, this follows kind of a susceptible, um, a susceptible population, and it kind of follows a different pathway in that you have people who have realized infections, you have asymptomology, pathogenic uh, infection, or people who are sick. There is the infectious or the infectivity model where you have symptoms associated and you either have convalescence to recovery, either from being infected, asymptomatic, or asymptomatic, and or you have people who leave the population through a mortal event. So the reading for this particular for the next section that we're just going to talk about is the Howell paper that I've linked on to Canvas. And so with that, we're gonna kind of just jump right into the pandemic that was associated with plague and see, if we can take a historical event that has already occurred, we can take all of the information from that and see if the SIR, we'll see how good of a fit the SIR model is to a particular infectious disease. So if you remember the second plague, also known as the Black Death, this is the one that lasts 400 years because this is the one that has acquired all those pathogenic properties that we talked about in class on Wednesday. And the reason it does is, well, once it does acquire all of those particular virulence factors, it has a much higher mortality rate. But again, the spread of this is a little bit more complicated because it's not a human to human direct contact spread of disease. I mean, it can be, but the vast majority of people who are sick because of flea bites. So, we think about one particular case study, which happened in Iam, England. So, in this one village, there were 270 deaths recorded over 14 months, and the population is somewhere hovering around 350 to 700. So, it gives you a mortality rate of between 40 and 80%, which is right around the same space we see bubonic plague having its mortality rate even still today. So, when we think about this stuff, we can think about, what are, can we take all this information, develop our understanding of what the R naught is, and does this give us a predictable model? Because of the acuteness of infection, there was no immunity to this particular bacteria at this time. So if we're looking at a true spreadable communicable disease, does that fit the SIR model? Um, so, once we consider the pandemic itself, what about after the epidemic, right? If you have if you have an epidemic that occurs and it's starting to go down, or if you still have a subpopulation of people who are infected that could continue to carry that particular infectious agent, what is the likelihood that you might get um, another population of susceptible people, especially after an epidemic that starts to wind down, causes mutations in that particular infectious agent, and then do you have another susceptible number of people that exists after the epidemic has finished? So, in order to get this, we think of this term, which is S infinity, or the susceptible population that exists after a particular epidemic has occurred. So when we consider the IM mortality and estimating the R naught of plague or in this particular um, clinical case study, we see here in June through October or the end of October. So we're talking about 5 months worth of information, right? We can plot the R naught of the infection against the susceptible population divided by the number of individuals that still remain after the first epidemic. And by tracking this information, we can find on this curve like what the R naught is of plague, and it hovers around somewhere about 1.7-ish. right? And here you go. Um, we know that R naught based on some algebra is in this case a natural log function of the number of susceptible people multiplied by um, the number of individuals in a population. And so if we consider how many people were left after the infection, right? There are 83 divided by that are left, right? So here, the 83 survivors. We divided that by the total population. This gives us our S, um, our sorry, our susceptible infinity over the total population ratio, and if we plug that into our new algebraic equation, we end up getting an R naught of 1.67, which I was close. I said 1.7, 1.67. Sorry. So, well, when we have this information, we now have R naught, right? We have an R naught. Um, we have our R naught of 1.67, and it seemed that when people have gone back and looked at cases of plague without intervention, plague is about 11-day infectious period. So, and this is because death occurs at day 11 of people who typically die of plague. So we don't know what B is yet. We don't know our beta, but we now know our gamma V uh um our gamma V term, because our gamma V term is 1 divided by 11. So, we have one infection that occurs over 11 days. So we plug this in, right? We have R naught at 1.67. Our gamma V term is 1 over 11. And we plug it in, and what do we get? About 0.15 is our beta term. That is our force of infection. So now that we have all this information, right? Sorry, keep hitting the button. Once we have all this information, we can finally set our susceptible population. We know what our total population is. We know from our beta in order how to calculate our infection that changes the infectious populace over time. And we now know the rate of recovery. So if we know how many people have recovered, we can then generate our understanding of what our over that same period of time change is. So, and so what do we see? So again, what we see is as we see the number of susceptible people go down, because we have people who are being infected go up, the observed deaths have gone up as people no longer are susceptible. But again, being susceptible has to infer that you either have convalesced from an infection or you've died, because you can't catch an infection once you've passed away. So as this downturns, as the number of infections downturns, the number of susceptible people also downturns, mostly because of either a lack of spread or a lack of critical community numbers in order for spread to continue to occur. So when we look at the lines of predicted deaths and number of infected people and number of susceptibles, and we overlay that to the inferred numbers based on our data, these lines track extraordinarily well, right? So this is one of those examples that the acuteness of the infection, the amount of infectious uh, the fact that the infectious component or the infectious contagiousness of this particular disease over its illness pathophysiology matches, it's not so surprising that uh, the predicted slopes of these particular lines overlay extraordinarily well with the actually observed susceptible, infected, and recovered individual populations. So again, this mapped from uh, May to October, but then we saw this other big swath of infections and cumulative numbers of deaths. So how could we have predicted this, or how well does this fit into the system um, from the second epidemic? Well, one thing that our first compartmental model doesn't consider and was probably difficult and has to be put into a different type of model is not only the number of susceptible people that occur after a particular epidemic that are still left behind, but also the fact that this is not a direct interface with humans, in that the presence of fleas and more importantly, infected fleas are where you start this whole process in the first place. So we have to consider the fleas, the passage of the fleas, and the movement of people all into the compartment that is important for initiating the SIR model. So when we consider this and we consider all the susceptible and infected parts of this puzzle, it's not just enough to figure out how many humans are susceptible or infected, also the number of rodents and the number of fleas that are susceptible and infected. All of these pieces have to then fit into the model, be fit into the model, right? Because you need to have when you're trying to think of the beta of the SIR model, it is in a sense a function of the susceptible individuals multiplied by the number of contacts with with an infection, right? So how in a sense, how likely is it that a susceptible individual will contract a particular infection based on the number of contacts with the right infectious hosts gives you an inference onto what beta is. And because, as we mentioned in last class, plague only causes plague, especially bubonic plague, if it's coming from infected fleas that were on mice, right? Both of these things have to happen before they go into this model. Both of these things have to be then input into the SIR model. So, whereas for the first epidemic and the beginning of the second epidemic, the SIR model fits extraordinarily well. We have to consider a different compartment model when we think about the end of the second one and why it was so much more and why it didn't follow the trend was because not only do you have these important competing factors, but also we have to think about where we are in time. And that includes the increase in travel, which also caused this secondary spike uh, in in number of cases of plague. So if we take all this information and we put it into the nine compartmental model, including the number of cases, the number of the relative population of mice, and we can kind of guess as to how many fleas per mouse. We put all this into the model. We get a model here which actually does eventually predict the number of real cases of plague that have occurred with an R with a Pearson correlation constant of over 0.9. So that's it for this. Here are your readings for next week. So please do these over the weekend or Friday or sorry, or Monday morning. They're Elite 2020 and Fraser 2022. And please, if you get a chance over the weekend to read the short book on pandemics and epidemics. And I will see you all Monday. Thank you, and look forward to seeing you guys next week.